Hello. Hello. Varipo here se. What I unmute mama mic yenyu tienza kuti tiripo tese here.
Yeah, se vadzoka.
Atsoka.
Tiripo.
Vanonga vakasikiwa vakomana vauye nekuti hey vamwe na8 tiri magadhi kana 8 o'clock tinoita kutotanga basa.
Evening.
Evening, how are you? Say,
How you say?
I'm okay. I'm good. Just the 6 of you.
Yeah.
yeah, maybe I need to.
That others will join us along the way.
Yeah, well, hoping so too.
Ndemera, mute your mic.
Maria, you were saying something. I was on a call and I wasn't listening in. What did she?
Yeah, I was saying Demira Mucho mic. She was unaware that the mic was on.
Just confirm to me, we had covered sequence diagrams.
Yes.
Class diagrams.
Class diagrams. I think we didn't cover this thing. This topic.
Okay. We'll start from class diagrams. In our previous lecture that we made physically, I think the last thing that we were talking about was system modeling. We highlighted the importance of system modeling as a way of representing requirements in a way that allows everyone to be clear on what exactly needs to be done. We discussed that there are several types of, there's several perspectives of a system that can be modeled. The behavioral perspective, the structural perspective, and so forth. About 4 perspectives of a system can be modeled. And we were now on structural models. What really is a structural model? It is a way, structural models of software display how a system is organized. Yes, Andrew?
Sorry, say I think Dinegenda Rasika. This lecture ICCT had.
No, it's not for ICCT.
All right. My apologies. Let me leave.
Much. Okay, I was using this same link for my lectures for Introduction to Computer Science. So some might get lost here, but today's lecture is a software engineering lecture. So if you are in here and you're not part of the software engineering class, please, this is not for you. Anyway, we're talking about structural models, and I was just about to say that these structural models are used to represent how a system is organized as a whole, how a system is organized in terms of components that make up that system, and the relationship that exists between those different components. So structural models can be dynamic, they can be static. There are different representations that show the different structures of models. When you create a structural model of a system, you are discussing and designing the structure of the architecture of the system, rather, how a system is organized as a whole. So architectural design is the next thing that we'll be talking about. Is very, very important in software engineering because it allows us to deploy. It gives us a way or means that we use to deploy a system at the end of the day. There are quite a number of structural models, but in the UML structure, the class diagram is the most common. What's a class diagram? I want to believe that you did databases at some point, and you discussed class diagrams. So class diagrams are used when developing an object-oriented system to model and show how classes in a system are related to one another. The associations between different classes in a system. So what's a class? It can be thought of as some kind of system object or entity. Then what's an association? An association is a link between classes that indicates that there's a relationship between these classes. So what are we saying? We're saying that each class may have some knowledge of its associated class. When you are developing models during the early stages of software engineering, objects represent something in the real world. For example, if you are developing a hospital management system, a real world thing in such a system would be patients, would be the doctors, would be the prescriptions, would be the doctors, and so forth. You need to identify all the real world objects that exist in your particular system. That frames the starting point of your class diagram. The class diagram can be expressed in at different levels of detail. Usually, when you are drafting these class diagrams, it's an iterative process. Like I told you, all system models are done iteratively. You don't start with the correct thing at the very first go, or rather, you will take your time improving your model until the level of detail is to your satisfaction. When you're developing a model, the first stage is usually to look at the world, identify the essential objects, and represent these as classes. So what am I saying here in a nutshell? I'm simply saying that whatever system that you want to develop, identify the essential objects or the essential entities that are going to be in that particular system. Those are then what we call the classes. The simplest way of writing this is to write the class name in a box. Like here, we have a class called patient. We have another class called patient record. The association is that there is a relationship between a patient and a patient record. You can simply note the existence of an association by drawing a line between the class. So if there is a relationship that exists between two entities, you represent that with a line. We will talk about cardinality later on, this one-to-one. Cardinality usually refers to the relationship that exists between entities, the type of relationship that exists between entities. So this diagram here is a class diagram that shows two classes, patient and patient record, with an association between them. When class diagrams become more detailed, they become, or they are known as semantic data models. So semantic data models, we usually use them to design our database. They are used primarily in database design. Why? They show us entities, their associated attributes, and the relationship between these entities. So class diagrams are mainly used to then construct a database in the database tables that should be in our database. This example here is of a class diagram. The class diagram consists of a number of entities. We have a consultant, we have patients, we have condition, we have general practitioner, we have consultation, we have medication, we have treatment, we have hospital doctor. So what are we saying here? We are saying that our patient, there is an association between a patient and a consultant. So patients are referred to consultant. And they are usually referred to consultants by general practitioners. A general practitioner will refer a patient to a consultant. Because this patient has a particular condition, they're diagnosed with a condition. Notice something, all the relationship or the associations in a class diagram have a unique name. You have a name, rather. There should be a name. Each association should be associated with a name. The association between condition and patient is diagnosed with. The association between a consultant and a patient is referred to. The association between a patient and a general practitioner is referred by. The association between patient and consultation, a patient attends a consultation. After attending a consultation, they are prescribed medication. They are also prescribed a treatment. When they are consulted, these consultations are usually run by hospital doctors. So this is a diagram that represents a class diagram for a clinic management system. Then let me now talk about cardinality. This relationship represents what we call a many-to-one kind of relationship. So many patients are usually referred to one consultant. In a town, for example, in Masvingo, we can have only one pediatrician or something like that. We might just have one pediatrician, but many patients can be referred to them. Right? Then again, many patients can be at a hospital. Many patients can be a general practitioner can refer many patients to some consultants. This is just a general practitioner. He might refer many patients to consultant. And then we have this relationship called many to many. Many to many. It's called the many to many relationship. What does it mean? It means that different patients, many patients have different the diseases that they suffer from, the different conditions that they can suffer from. So all those patients, the different patients can be diagnosed with many different conditions. So the relationship that exists between a condition and a patient is a many-to-many kind of relationship. Similar to patients and consultation, many patients can do many consultations at a clinic. Many patients can attend many consultations at a clinic. So that's what we call cardinality. It should be reflected on your class diagram to show the kind of relationship that exists between the two entities that you would have identified. When showing association between class, it is convenient to represent these classes in a simple form. You can, of course, define the class in more detail, but at a later stage. Initially, you just start with the class name. You don't even have to mention the attributes and so forth. This will enable you to capture all the classes that are in a system. But later on, as you add detail to your class diagram, you need to add more information. Information like what? You need to add the attributes of each class. Like the class patient, what attributes does it have? It has attributes like the name of the patient, their surname, their ID number, DOMA attributes or characteristics of an entity that you need to add. You also need to add the operation. What things you can request from an object. I'll show you in the next page. For example, a patient object will have attribute address. You may include an operation called change address, which is called when a patient indicates that they have moved from one address to the other. This is a typical, well-detailed class called consultation. This consultation class has several attributes. Like what? Like it is an attribute called doctors, an attribute called date, an attribute called time, clinic, reason, medication prescribed, treatment prescribed, voice notes, transcript. And these ones are actions. These are possible actions that can be done, and usually they relate to changing the attributes from one form to the other. For example, we can have a new consultation. That's an action that can happen under consultation. We can have a new prescription that is prescribed. We can have a new record notes when the doctor records notes about the ailments. We can have the transcribe action. So this now represents the full structure of a typical class. Now, you then draw another class and show the relationship that exists between the different classes with the aid of a line. For example, instead of this simple consultation with just which is quite shallow like this, you are then including your consultation class with all this information. Saka, it becomes so much easier when someone is then writing or implementing code. They know what attributes to consider. If they are designing a table to store all these records, they know exactly how many rows they are supposed to include for the class consultation. That's structural models. Let's move on to behavioral models. This is another aspect of a system that can be represented. Behavioral models are models, they model the dynamic behavior of a system when it's in execution, how the system moves from one state to the other when it is executing. They show what happens or what is supposed to happen when a system responds to a stimulus from its environment. You can think of this stimuli that stimulates the change as one of the following. It can be data. Some data arrives that has to be processed by the system, or it can be events. Some events happens that trigger system processing. Events may have associated data, but this is not always the case. So most businesses system are often driven by data, not necessarily events, but some actions are driven by events. For example, let me give an example of for a system that is driven by events. Think of a security system that monitors the environment for intruders. The system can only start processing things when the system is triggered by the event of an intruder coming in. That's when processing starts. But we are saying that most systems are not like this. Most systems are rather data processing system where you need to add data, and once you've added that data, processing begins. Usually, in this case, for data processing, it involves a sequence of actions on the data and then a generation of an output. Here is an example of a data processing system, a phone billing system. So this one, the phone billing system will accept information about calls made by a customer. It then calculates the cost of these calls and then it will generate a bill to be sent to the customer. By contrast, real-time systems are often event-driven with minimal data processing. For example, a landline phone switching system responds to events such as a receiver off by generating a dial tone. Someone has put down the phone. What does the system do? If it notices that the phone has been put down, as if it's engaged but it's not engaged, it will automatically generate a dialing tone so that people can still call. The pressing of keys on a handset by capturing the phone number, etc. We call it, we want to talk about the latter, data-driven modeling. We said there's event-driven modeling and then there's the data-driven modeling. With data-driven models, with data-driven modeling, we are modeling the sequence of actions involved in processing data and generating some kind of output. They are very useful. The data-driven models, they are useful during analysis of requirements, as they can be used to show end-to-end processing in a system. There are quite a number of these data-driven modeling techniques that are used, but the data flow diagrams is one of the most famous data-driven modeling models ever developed. And up to this date, it's still very famous and mostly used in software development. So you need to know how to make a data flow diagram. You have no option there as a scientist. Data flow models are useful because they track and document how data associated with a particular process moves from the system. This also helps analysts and designers to understand what is going on in a system. Data flow diagrams are simple, intuitive, and is usually possible to explain them to potential system users who can then participate in validating the model. So your data flow diagram, it should be as simple as possible, so that you can be able to explain to ordinary users and then they follow what you are trying to do. If you make it as simple as possible, it becomes possible for these system users to correct you and give you guidance on how it's supposed to work in case you would have made some errors. If you remember well, I said that you guys are not experts in accounts, neither are you experts in developing or in the school administration things. But you might be asked by the head to design a system to administer a school. You might be asked to design a system to do some payroll, to do some accounting tasks, etc. So by modeling the system that you have in your mind, you can then ask the users kuti zvandiri kutraya kuillustrata padiagram iri ndizvo here, ndo mafambiro anenge achiita data here musystem. Anokuudza ivo, because they are experts, they are going to tell you that no, this is supposed to be done this way, this is supposed to be done that way. This diagram here is a simple illustration of a data flow diagram with a very little detail. This data flow diagram, I have separated, I've put separate entities. For example, here you can see customer, customer, customer. 3 times you are seeing the entity customer. 2 times you are seeing the entity supplier. In a real data flow diagram, they should be, if there's an entity called customer, it should just be represented once. If there's an entity called supplier, it should just be represented once. So we're saying that this is a video rental company, that one that we were talking about the other day. So we are saying that a new customer is created. They want to join the club, so we create a new customer. When we create a new customer, here is the process of creating a new customer. The files of the new customer are then stored in the customer file. So this symbol here represents the store, a data store. This symbol here, usually with a horizontal line, or in this case is kind of slanting, cutting some edges of this shape here, we call it the entity. This now, the rectangle shape represents the process, a process that is happening within a system, right? So we have this process of creating a new customer, and then that created customers records are saved in the customer file. Same applies to supplier. We can have a new supplier. Of course, I didn't model it here. It would be linking new create new customer stroke supplier. Yeah. To register a new supplier. We have this process again within our system for data, for stock control. We have another process here for loading the video. And we have another data store here for stock, video stock. So this is a very simple data flow diagram that shows the data that is flowing from a customer into our system and from suppliers into our system. So there are stages, or there are things that you need to do when you are constructing a data flow diagram. One of the first things that you are supposed to do is to identify all processes. Where is data being processed? You need to list them down. All instances in which processing occurs. So each data flow into the system must be received by a process. That's one trick. Each data flow into the system must be received by a process. When you are capturing customer records, that's a process. When you are receiving an invoice of payment from a customer, that's another process. When you are receiving new titles of CDs or DVDs from supplier, that's another process. So the trick here is you need to identify all the data that is going to flow from outside into the system. That's a process. You just need to now write down the name of that process. And then for each data flow into the system, examine the documentation about the system and talk to users to establish a plausible process of the system that receives the data flow. Each process must have at least one output data flow. Each process must have at least one output data flow. We are saying that processes, usually when data is being processed, usually there is data that is flowing from that process to something else. That should be represented in a data flow diagram. Draw the data flows between external entities and processes. Identify data stores by establishing where documents or data needs to be held within the system. Add the data stores to the diagram, labeling them with their local name or description. That's how you construct a data flow diagram. You also need to add flows flowing between the processes and data stores. Tangachiti ma-association kana kuti ma-line ari kujoina between ma-process nema-entities kana kuti ma-entities against the entities. You need to add the data flows flowing between these processes and data stores. Each data store must have at least one input data flow and one output data flow. So every time you identify a data store where data is being stored, obviously information is being moved into the data store. And at the same time, information is going to be moved from that particular data store to the process. Say you are keeping files as customer records. We obviously need to use them one day. So those customer records are going to be stored in our customer record entity. And then information flows when we need now to access the patient, the customers that we have in our database. We are going to do the reverse now. Information is flowing from the data store into the process. You need to check the diagram. Each process should have an input and an output. Each data store should have an input and output. Check the system details to show if any process appears to be happening for no reason. If it's just happening for no reason, then there's something wrong with your system or with your diagram. Before we move on to event-driven modeling, could there be any challenges? Could there be any questions? Any questions so far? Okay, I'll proceed. We move on to event-driven modeling. Like I said, some actions or some systems are triggered by certain events happening. We call it event-driven modeling. In event-driven modeling, systems respond to external and internal events. It is based on the assumption that a system has a finite number of states and that events may cause a transition from one state to another. For example, an air conditioning system. A valve may move from the state valve open to the state valve closed when an operator commands is received. Okay, a system, okay, this one is a system controlling a valve. It may move from a state valve open to a state valve closed when an operator commander is received. Think of an air conditioning system. If a room reaches a particular temperature, the system may, because the stimulus, which is a certain temperature, has been reached, the system starts executing. The fan starts running for the air conditioner, and the temperature starts to reduce. If the temperature reaches again the lowest temperatures indicated, the aircon will stop producing the cold air and so forth. That's event-driven modeling. We call this in computer science, what name do they? We call them, I'm forgetting the term that we term them, but they are real-time systems. They usually respond to external events. So event modeling was introduced in real-time design methods such as those proposed by Watt and Mello in 1985 and Harrell in 1987. The Unified Modeling Language supports events-based modeling using what we call state diagrams. State diagrams. So state diagrams are the ones that we normally use to model event-driven modeling. So a system is either event-driven or it's data-driven. It can be both data-driven and event-driven. So there are some systems in which you are supposed to draw a data flow diagram, whereas in other systems you are supposed to draw a state diagram. You can have a system drawing both the state diagram and the data flow diagram because these systems are different. One is event-driven, another is data-driven. So what are state diagrams? These are like data flow diagrams, only that they are specifying actions that will cause a transition of a system from one state to the other. So state diagrams show system states and events that cause transitions from one state to another. They do not show the flow of data within the system. But of course, you may include additional information on the computations carried out in each state. And a microwave, a simple microwave oven example is used to illustrate state diagram in this lesson. This simple microwave has a switch to select full power or half power, a numeric keyboard to input the cooking time, a start or stop button, and an alphanumeric display. The assumption that I've made here is that the select power button, I've assumed that the sequence of actions in using the microwave is as follows. You select the power level, either you select a half power or full power. You then input cooking time using a numeric keyboard. You then press start and the food is cooked for the given time. For safety reason, the oven should not operate when the door is open. And on completion of cooking, a sound should be produced to show that we are done. The oven has a very simple alphanumeric display that is used to display various alerts and warning messages. This is a typical example of a state diagram. We are saying that we are waiting for the stimuli. So what will be displayed there is just the time, the local time. If a user presses full power, the power is set to 600. Otherwise, if a user presses half power, the power is set maybe to 300. But since we have not started cooking or grilling, whatever we are doing in the microwave, you can convert from half power to full power or vice versa. Wawa selector full power, unogona kuchinja. Also selector half power, and also selector full power. But whatever action you would have done, you need now to set the time that the user is going to cook their food. This is a numeric number. After running, just like in an ordinary microwave oven, unogona kudefrosta zvinhu zvako for 2 minutes. After 2 minutes, hazvisati zvadefrosta, you can still run again. So I've made this process repetitive, as you can see. Kuti munhu anoramba achiseta time yake yaanoda kusvika zvinhu zvake zvaita. But this the system is disabled if a door is open. You try to press, nothing will happen because the door is open. Once the door is closed, the display ready is shown and you press start. The operation is completed, the door opens, or you get a beep. So this is a state diagram that shows how a simple microwave oven works. I think I gave you an assignment that required you to draw a state diagram of a particular system. I'm no longer sure what it was. But this is how I expected your diagram to come up like. So in state diagrams, rounded rectangles represent system states. They may include a brief description following do of the actions taken in that state. As you can see, this is a simple description of what's happening. Do get number, set the time. Do set the power. Do display waiting. So you can include this information in your state diagram. The labeled arrow represents the stimuli that forces a transition from one state to another. You can indicate starts and end states using those field circles as in activity diagrams, like we're doing in activity diagrams. So a field circle like this represents the start of the process, and then a field circle inside a circle represents the end of the process. So that's system modeling in a nutshell. You already have this. Just look at this summary when you get time. This one was the assignment that I gave you. The question required you to draw a state diagram of the control software for a DVD player. Any questions so far?
We are following. See.
Okay.
Let's go.
We now want to move on to architectural design.
Hello, Sam.
Hello, you just hold on. I'm opening the presentation.
Hello.
Hello, I'm opening the presentation. Just hold on.
Okay.
So this is what we are going to talk about. We are going to talk about architectural design decisions. We are going to talk about architectural views. We are going to talk about architectural patterns and application architectures. So when you have finished the modeling, designing how your system is supposed to operate, you are supposed to then come up with the architecture of your system as a whole. We call it architectural design. When you are coming up with an architecture, there are some decisions that you need to first make before selecting the particular architecture that you want to use. So we are going to be discussing that, and we'll discuss the different views. There are so many of them, but for each system that you are coming up with, you select what is appropriate to the particular system. In other words, we are discussing a lot of architectural designs, which are of course so many, but when you are working with a system, you are going to choose a particular system design. Euphenia, Epiphania.
Epiphania.
Your
Okay, let's
name
continue.
is. Why are you raising your hand?
I'm just familiarizing with this app. Sorry.
For your name. Okay,
I'm
it's fine.
sorry.
No problem. How do you spell your name?
I'm Epiphania.
Alan ari kunditi ndiri wrong.
Never say that. Say. Just corrected you.
No, what she said is what I said. You have what anons Ephenia. What anons
I was just imitating what you were saying yesterday. She is Epiphania.
you were mocking me about what I was saying yesterday. I see. Okay. Okay. We want to talk about architectural design. What is it in the first place? What is architectural design? This is
But my
concerned.
slides are showing.
Are you sure?
Azvichaoneki zvazvidiki diki izvi. Taita chiverenga.
Indakatoisa screen rose and kutobudisa ndichiona screen rose. Is this the same question?
Tudiki diki hatisi kuoneka kuti.
Yeah, zvatisiyana nepekutanga pai.
Tanga tichiona. Izvino hazvichaoneki. Saka tichachiverenga zvinonzwisika zviri nani.
Yeah, right.
Yeah, right.
Zvona ndakangoita wani.
Zvangu hazvina. Zvangu hazvina vedu.
Yedu yaita.
Maybe yaera yefoni zvaita izvizvesi.
Kuona
Now,
pani.
era yefoni.
Zvaita.
My idea was not Nokia, but it has not said.
Alan, chako chivhivho ichocho.
Architectural design. Zvazoita.
Yes.
Saka vangu vachirevesa vangaitani kuma-iPhone kuma I want iTel.
My iTel.
Okay.
Asi posiri pamavhiri neITel iyoyi.
What is architectural design? Architectural design is concerned with understanding how a software system should be organized and designing the overall structure of the system, of that particular system. So it provides a link between design and requirements engineering, as it identifies the main structural components in a system and the relationship between them. The output of the architectural design process is an architectural model that describes how the system is organized as a set of communicating components. It's an essential activity that needs to be done in the software development process. As soon as you are done with your system models, you need now to come up with an architectural design that shows how your system is structured as a whole.
Hello, sir.
Yes. Any question? Are we still together?
Let's move on.
Okay.
We are following, sir.
Just to maybe give you a heads up on what I'm talking about when I'm talking about architectural design, here is a diagram that shows a particular system. In this system is a system of a packing robot control system. This system is like a robot system that identifies objects and then packs them. So this is how the system is going to be. This is how the system is as a whole. We have a vision system that identifies objects. Then once the objects are identified, we have an arm controller which moves the arm to pick the object. This arm controller has a grip controller depending on what the object is so that it applies the correct grip. Once the object has been identified, the object is placed in the correct package. Once the object has been placed in the correct package, it is then placed in the conveyor belt so that it moves along the chain. So here I was just trying to model the architecture of a packing robot control system. So whatever system that you then want to design, you should show how it looks like as a whole and how it might work with other currently existing systems. That's what we are talking about when we are talking about architectural design. Let's talk about abstraction, architectural abstraction. Architecture in the small is concerned with the architecture of individual programs. At this level, we are concerned with the way that an individual program is decomposed into components. Sorry?
Mutai mamic yenyu mana kana make sure that your mic is muted so that we can follow. tozongoita unmute kana tichida kucontribute.
Mute all.
Let's move on, sir. Sir,
I moved. I think I lost my. How come I can't even find my PowerPoint that I was running? Sorry to that. Am I still sharing something?
No.
No, hapachisina.
Yeah. Zvavapo.
So we are saying that if we are talking about architecture in the small,
taita zvidiki.
we are concerned with the architecture of individual programs. But when we are talking about
Taita
architecture,
zvidiki futi.
Pisha mwari. Chimbomira unoteerera zvimwe unomva mwari.
from my end, it's
Ya, zvabo.
hapana zvandamboita.
Ya, inyaya yekwandiri wedu hendiwisewo ndiri mumuti.
Architecture in the large is concerned with the architecture of complex enterprise systems. That includes other systems, programs, and program components. These enterprises can be distributed over different computers and so forth, over different computers, and they can be managed by different companies. This is a system architecture in the large. So it really depends on what kind of system that you are working on. Let's talk about advantages of representing a system. It's architecture. What are the advantages? One, it enables you to communicate with the stakeholders. When you design the architecture of a system, stakeholders, for example, the clients, owners of other systems that you are going to be integrating your system with, and so forth, all those, you can then initiate conversations with all those different stakeholders to facilitate communication. Then architectural representation also helps in system analysis. It means that the analysis of a system, you are checking, you can then check whether the system is going to meet its functional and non-functional requirements as required. So it helps in the system analysis. You analyze the system as a whole to see whether it's going to meet its requirements. And then large-scale reuse. Architectures may be reusable across a range of systems. Representing your system as architecture can help even others who then want to integrate with your system later at a later stage to show the relationship that will exist between their systems and yours. That's the large scale reuse. There are so many architectural representation that can be used. We can use simple informal block diagrams showing entities and relationships. These are, of course, the most commonly used methods for documenting software architectures, the use of block diagrams. However, these have been criticized because they lack semantics. They don't show the types of relationship that exist between entities, nor the visible properties of entities in the architecture. It also depends on the use of architectural models. The requirements for model semantics depends on how the models are used. So this is the simple block diagram that I'm talking about. It's called the box and line diagrams. It's very abstract. They don't show the nature of components and relationship, nor the externally visible properties of the subsystem. But they are useful for communicating with stakeholders for project planning. What are they used for? These box block diagrams. They can be used as a way of facilitating discussion between a system. It provides a high-level architectural view of a system. Then they can also be used for documenting an architecture that has been designed. Let's look at architectural design decisions. What makes one come up with a particular architecture? So architectural design is a very creative process. So the process differs depending on the type of system being developed. However, a number of common decisions span all design processes, and these decisions can affect non-functional characteristics of a software. So these are some of the questions that you ask yourself when you want to come up with a system architecture. These are the design decisions. These are the questions that help you come up with a architectural design. Is there a generic application architecture that can act as a template for that system that is being designed? Hakuna zvimwe zvakamboitwa here zviri very close to what you want to do that you can then use as a template. That could help you on the architecture that you are going to choose. How will the system be distributed across hardware or processors? Is it your system going to be operating in one computer, or it's going to be multi-processed in several computers? What architectural patterns or styles might be used? What strategy will be used to control the operation of the components in the system? How should the architecture of the system be documented? What architectural organization is best for delivering non-functional requirements? How would the structural components in the system be decomposed into sub-components? What will be the fundamental approach used to structure the system. So these are some of the questions that you ask yourself. Alan?
Alright, ndiri kuti maslides aya hachasi kufamba here kana kuti kufoni kwangu yakangobudisa architectural abstraction.
Ingoteerera wanditi teerere pari.
Anaufunza iwe mune.
I'm on slide rakanzi architectural design decision.
Tichiri pa-architectural abstraction, right? The first slide.
Is this is it the same question?
Yes.
It's not
Yes,
moving.
Yes, it's not moving.
Okay, let me do it this way.
Hey, are you there?
Yes, I'm there. I want to share this presentation on WhatsApp, on your WhatsApp platform, so that you can follow from there in case there is a problem.
Okay.
Okay, sir.
Okay. I'm seeing my messages to WhatsApp. Hanzi network iri kunetsa dai zvaitirwa paWhatsApp. It's true. Kunetsa here network.
Sekutodaro.
Network inonetsa zvekutodaro.
WhatsApp iri
WhatsApp inoitika sei live meeting?
taingoita last semester taingoita seizvozvi tiri kuWhatsApp.
Aita nani?
Ndakanganwa lecturer wacho.
We shared the presentation.
Communication skills.
Digital design. Do you see it now?
Architectural abstraction.
Oh. Slide rakanzi architectural design decision.
I'm seeing architectural abstraction this end.
Have I stopped sharing?
Yes.
Muri kuona pakanzi chii? Architectural abstraction ndo pamamuchiona.
Mhm.
Muri kuona pakanzi architectural abstraction handiti?
Yes.
Uchiri kupaona?
No, nothing is displayed now.
Chaziviwo zvakuitika. Saka paWhatsApp maishare sei mawe?
Guys, there's a PowerPoint.
Aingoita WhatsApp aingova zvepaWhatsApp echinse tati tisingamboshare mascreen taingotaura like a group call, group video call.
Okay,
Because
let's
we
do
said
this. Let me share my screen.
Yeah, zvakuhamba manje.
What about this?
Zvakuonekwa.
Okay. Um, so I'd said these are some of the questions that you need to ask yourself in coming up with an architectural design. Now let's look at the different architectural views, how you view different architectures. So what are these? What are architectural views? And what views or perspectives are useful when designing and documenting a system architecture? What notations should be used for describing architectural models? Each architectural model only shows one view or perspective of a system. It might show how a system is decomposed into modules, how the runtime process interacts, or the different ways in which system components are distributed across a network. So these are the different views of system architecture. We have what we call a logical view of the system architecture. We have a physical view of a system architecture. We have a process view of the system architecture, or a development view of the system architecture. What's a logical view? A logical view shows the key abstractions in the system as objects or object classes, whereas a process view shows how at runtime the system is composed of interacting processes. A development view, on the other hand, shows how the software is decomposed for development. A physical view shows the system hardware and how software components are distributed across the processors in the system. Representing architectural views. Some people argue that UML language is appropriate notation for describing and documenting system architecture. In my opinion, I think it's not the best because of the abstractions in UML. Rather, there's a language that was designed, which is called the Architectural Description Languages, ADL. These have been developed, but however, it's not widely used. I think it represents system architectures in a better way. So there are several architectural patterns Architectural patterns are means of representing, sharing, and reusing knowledge. An architectural pattern is a stylized description of good design practice which has been tried and tested in different environments. Patterns should include information about when they are and when they are not useful. Patterns may be represented using tabular or graphics description. So this as it moved to slide the model view controller pattern.
Yes.
Okay. The model view controller pattern separates presentation and interaction from the system data. The system is structured into three logical components that interact with each other. The model components manages the system data and associated operations on the data. Then the view, these are the three logical components, the model, the view, and the controller. So we are saying that they are structured, the system is structured into these three logical components. We have the model. What the model does is it manages the system data and associated operations. The view, on the other hand, defines and manages how the data is presented to the user. The controller, on the other hand, manages user interaction. For example, what happens when a mouse is clicked or when a key is pressed? It passes these instructions to the view and the model. We have an example in the next page that shows the architecture of a web-based application system organized using the MVC pattern. When is it used? When do we normally use the model view controller pattern? It is used when there are multiple ways to view and interact with data. It is also used when the future requirements for interaction and presentation of data are unknown. So what are the advantages? It allows data to change independently of its representation and vice versa. So you can change the way data is represented later on. It supports presentation of the same data in different ways, with the changes made in one representation shown in all of them. The disadvantage is that it can involve additional code and code complexity when the data model and interactions are just too simple. So this diagram here represents the model view controller of a web page. The controller, we have the three components, the controller, the view, and the model. The controller maps user actions to model updates and selective views. The view, it renders the model, it requests model updates, send user events to the controller, and then the model, it encapsulates application state and notifies a view of state changes. This now is a real software, the web application now. So this is how the controller, the MVC works. And then here is how it actually works in a real system. So we have our browser here, and it's being represented by the three components, the controller, the view, and the model. What does the controller do? We have the HTTP request processing, application-specific logic, and data validation. The view, it shows the dynamic page generation and form management. And then the model, the business logic, and the database. We also have what we call the layered architecture. This one is not very common. The MVC pattern is not very common. Then we have the layered architecture. In the layered architecture, it is used to model the interfacing of subsystem. Instead of organizing the system into three components, the layered architecture organizing system into a set of layers which support each other, each of which provides a set of services to the other. It supports the incremental development of subsystem in different layers. When a layer interface changes, only the adjacent layer is affected. However, often artificial to structure systems in this way. It's not very, very practical. I want you to think of the Kanamakaita module on the internet. Think of the OSI model. It's a typical example of a layered architecture where layers above and below support layers that are above. So the description of the layered architectural pattern, it organizes the system into layers with related functionality associated with each layer. A layer provides services to the layer above it, so the lowest layers represents core services that are likely to be used throughout the system. There's a diagram that I will show you later on. An example here, a layered model of a system for sharing copyright documents held in different libraries. When do we use the layered architecture? When we are building new facilities on top of existing systems. When the development is spread across several teams, with each team responsible for a layer of functionality. Then what are the advantages? It allows replacement of entire layers as long as the interface is maintained. So it's sort of modularizing or designing using modularization. Each layer can be thought of as a module, and then we have different teams working on different layers. The disadvantages is that providing a separation between layers is very, very difficult. Also, we might identify a layer on the top echelon of the layer structure, but in practice, that layer might be interacting directly with the layer that is on the bottom of the list of layers. How then do you represent that in the layered architecture? It becomes very difficult. So this is a typical example of the layered architecture, the generic layered architecture. I think the design of operating systems are structured like this. We have the user interface at the top there. We have user interface management and authentication and authorization. We have the core business logic application functionality or system utilities. And then the bottom layer is system support. This is an island system. It's an application designed to support online learning, whatnot. And I've just represented it as a layered architecture there. We have our browser-based user interface, the iLearn application. It's browser-based. You open it on a web browser. But below it, we have configuration services. Configuration services include group management, application management, and identity management, where users need to verify themselves and so forth. And then the layer below the configuration services is the application services. Here, within this application, there are layers such as email, messaging, video conference, all those kind of applications that are provided by any typical e-learning system. Then Down here, we have utility services as the base, like the authentication, logging and monitoring, interfacing, user storage, application storage, what. So this is a typical layered architecture. Then we also have another architecture called the repository architecture. In the repository architecture, we are saying that subsystem must exchange data. And this exchange of data can be done in two ways. One, shared data is held in a central database or repository and may be accessed by all subsystems. Or each subsystem may maintain its own database and then it passes data explicitly to other subsystems that might have requested it. But when large amounts of data are to be shared, the repository model of sharing is most commonly used because it is efficient in for data sharing mechanisms rather than a system where a subsystem maintains its own data. So it's called the repository architecture in that the data is being stored in a single repository. So in the repository system, all data is managed in a central repository that is accessible to all system components. Components do not interact directly, but they only interact through the repository. There is a diagram that I will later explain, which shows the repository model. When do you normally use the repository pattern? You use this when you use it when you have a system in which large volumes of information are generated that has to be stored for a long time. You may use it in a data-driven system where the inclusion of data in the repository triggers an action. What are the advantages? One component can be independent. The system is designed in such a way that subsystems are completely independent from other subsystems. So other subsystems do not need to know the existence of any other subsystems when being developed. Even changes that are made to components or subsystems do not affect others because these subsystems only interact with the repository or with the database. All data can be then managed consistently as the data is in one place. The disadvantages is that the point of failure of a system is centralized. If the repository fails, then the whole system goes down. And then there may be inefficiencies in organizing all communication through the repository. And then probably distributing the repository across several computers may be difficult. This is a typical structure of a repository architecture. This is a development environment. You have your project repository here. This is the central repository of your project. And then we have components that help you in the development environment. You have UML editors, you have code generators, you have a Java editor, you have a Python editor, you have a report generator, a design analyzer, a design translator. All these components, they don't need to know the existence. For example, if you are good in Java, you'll be just using this Java editor. There's no need for this Java editor to interact with the Python editor and so forth. If your code generator, you can work with this code generator without necessarily interacting with any of these other components. That's the repository architecture. Then we have another architecture. This is the commonly used architecture in the development of systems, the client-server architecture. The client-server architecture, so, well, the repository architecture and then the client-server architecture are the most commonly used architectures in the design of systems. The client-server architecture, a system model, it shows with the distributed system models, they show how data and processing is distributed across a range of components. Of course, these different components can be implemented on a single computer or they can be implemented on multiple computers. Standalone servers provide specific services, set of clients which call on these services, and then we have a network which allows clients to access servers. These are the components that are in a client-server architecture. This is the description of the client-server pattern. In this, we have a client. It is used in a client-server architecture. The functionality of the system is organized into services, with each service delivered from a separate server. Clients are users of these services and access servers to make use of them. We have a client-server architecture diagram that I will show you later on to try to model or represent this. When do we normally use the client server? When data in a shared database has to be accessed from a range of locations. Because servers can be replicated, this may allow it to be loaded on a system, on various systems. The advantages is that the model can be distributed across a network. General functionality can be available to all clients and does not need to be implemented by all services. The disadvantages are that each service is a single point of failure. So it's susceptible to denial of service attacks or server failure. Performance can be unpredictable in client-server architectures. So we have this a client-server architecture for a film library. Think of maybe services offered by Netflix or some other video rental organization. Clients want to access videos or movies. So these movies, Netflix stores its services on different servers. For example, there can be a catalog server, there can be a video server, there can be a picture server, there can be a web server. So the services that are offered are scattered across several servers that can be accessed via the internet. But to the client, you can't tell that the services are scattered across the different servers. So the advantage of this structure is that if this one, for example, the catalog server is down, yes, the clients can't access catalogs to see the movies that are on offer, but they can access some videos that are in this particular server or some servers that are in this particular, they can access some videos that are in this particular server. So that's the main advantage of the client service architecture. You are trying to distribute your services across multiple servers so that you reduce the likelihood of one point of failure associated with the repository architecture. So this architecture, like I said before, is mainly used by many organizations. For example, Vana Facebook, Vana Google, Gmail, and so forth. They use this kind of architecture. In some cases, the same information that is held in this server is also held in this server, is also held in this server, or something like that. Such that even if this server is down, still different clients can access their information from this particular server. It's called the client-server architecture model. Then we have the pipe and filter architecture. I'll read more on this. This is an example of the pipe and filter architecture. Here I was trying to put more detail, more explanations, so that people really understand the concept of architectural design. Again, I think it's for naught. This is the layered system architecture. The architecture of a meant case system. I was just re-emphasizing on this. This is the layered architecture, explaining how the different architectures are used in different systems. This, I was now explaining the repository architecture for a language processing system, adding more detail to what we have already discussed. This pipe and filter architecture, and these are the key points. And this ends the presentation on architectural design. The next thing that we would have to discuss is on component design. So tomorrow I will start again presenting. I will start with the presentations and I will present some elements of component design. And then that other group 6 will also make their presentation tomorrow. This marks what I had for you today. Are there any questions?
Yeah, the content is just too much. Yes.
Pakashata
No questions. Say my tabasa. It was a PowerPoint presentation.
It's quite a lot because there are just a lot of different architectural design. In the exam, I could ask you about the pipe and filter. I could ask you about the repository architect. I could ask you about the layered architect. So you can't not know all of them. You need to know all of them. But then we're saying when you are then in the industry, when you want to develop your software, you are just going to be focusing on one architecture that suits whatever application you are developing. But as a student, you need to know all of them because I can ask about any of them.
Yeah, pane basi.
All right, sir. Ini ndoda kubvunzawo zvangu.
Sure.
Topresenta sei zvimwe ine hangu haasati namboshandisa DC.
Shandisa PowerPoint presentation. Zvinhu zvenyu munozvisa kuPowerPoint mongopresenta mapresentero andiri kungoita iwawo.
You're using which device?
handiri kushare screen rangu handi.
You are presenting using your laptop.
Yes, I'm using a laptop.
Okay.
Ukauya apa ndipo panoshewa napapo, ukatokilika apa wototi share.
Vakanzi chii?
Pakanzi chii?
In my
All
case, pakanzi stop sharing because I'm already sharing something. This is the microphone.
Nichikuita chokwadi inangu ida kutobatsirwa kuti
Your group members will help you. So you click here and then you share your presentation like what I was doing. You can just share your screen. If you are having challenges like what I was happening in my case, Papa, ndakanditi share just a particular screen, but computer yanga ichimbovhexika yokanganwa kumuvha. So ndangozoti rega ndingoshare screen rese so that memuchiona zvose pese papeji randiri nemiwo mune muchitopaona.
saka ndotanga ndatoinstalla that thing mumachine mangu.
Inonzi Teams. This application, yes, it needs to be installed in your computer, but it can also work in a web browser.
Okay.
But it's better if you use it as an application. You install it as an application on your device. You can even present using your own your phone. It can still work.
I can share my screen using
Yes, you can share your screen and then you start reading your slides at phone mark.
phone ndoenda nepapa sikupaona peshare screen phone.
Epifani, unozoita, you may explore, my guy.
Utakanganisei?
I will help you. I will not kanganisa, but we want to do other things.
Chiripo pakanzi share phone. Chiripo chibhara chiri paside nemicrophone. Let me stop sharing. Maybe you will find it then. Thank you for attending. Can I just say your faces before you go? I was recording this. I will share with you a link to this so that those who didn't manage to attend can view, can play at their own time. Okay. Hello, everybody. Maria, you are still in the dark today.
Yes.
Kuwerewo tsitsi vanhu vekuzesa.
Pakaipa.
Sibongile hakuna magetsi. UP feni hakuna magetsi kugogwe.
Hakuna kugogwe.
Ndosaka wanga usingaoni button cheshare hanti. Because uri murima. Nyangadza, how are you? Ko Alice unenge uri mumagumbezi wani? Apa wakamute apa uri kutaura tisitombonza zvinotaura. Angela, how are you? Hi. See you tomorrow.
I'm good, sir. I'm good.
All right. Diana,
Ndini se.
wagona kushare screen. Okay, Rachel, how are you? Where were you yesterday?
I had network challenges yesterday. We had lost data, so I need to one.
Okay. Bye-bye. See you. Have a good night. And work on your presentations, Apere.
Thank you.
Thank you, sir.
All right, I'm ending the meeting now.
Thank you, sir.
Okay.
Sleep well.